disturbing trend that I'm becoming one of the older people at conferences, and and I especially noticed that here. It's really great to see all the much younger people that are really driving this field right now. So today I want to sort of revert to some of the theory discussion a little bit yesterday and the previous days about the origin of optical and X-ray emission in TDEs. We've heard this, sort of dichotomy presented that either the optical emission is powered by colliding streams or it's powered by accretion onto the black hole being reprocessed. And this sort of scenario or setup I'm going to describe is sort of a hybrid between these. I would say I think it's kind of both. I think stream collisions set up the initial conditions to feed the black hole, but I don't necessarily think that the energy at early times necessarily has to be released very close to the black hole. It may be from the contraction of an extended object. So it's the gravitational energy released from some extended point as it contracts that could power some of the optical emission. And this is actually 19th century physics, potentially aspects of it going back to Kelvin and Helmholtz. But on the other hand, I agree with the sort of geometry that Jane has been describing in terms of these reprocessing scenarios. I think that's going on as well. So everyone in this conference knows what tidal disruption events, but just to review, we have a star that's coming in essentially on a zero energy orbit most of the time. Gets disrupted, half of the star gets unbound, half of it stays bound. Roughly the amount by which it's bound is given by the gravitational potential over the size of the star. And if you calculate the orbital period of that specific binding energy, it works out to be about a month, which is, of course, the time that the most bound material comes back. But there's also matter that's even closer to zero energy, which comes back at progressively later times. And this is what gives you this t to the minus 5/3 decay, which, as we know, the fallback rate itself can be highly super Eddington, especially for lower mass black holes. And sort of everything I'll describe in this talk is going to be more or less based around a solar mass star, so you sort of have to scale with the stellar properties. As we heard yesterday, a lot of those scale out in many of these relations. So the sort of old picture when I was starting in this field was that, okay, the streams come in, they very quickly or somehow collide with one another and form this compact accretion disk, and based on the angular momentum of the tidal radius, it should form at close to the circularization of the material should be close to the tidal radius. And of course, we all know if you have thin disk emission from this radius at these accretion rates, it should be peaking in the soft X-rays or far ultraviolet. And indeed, many of the initial TD candidates were detected in these wavelengths. But then we had this sort of unexpected, when we started discovering optical flares, this unexpected fact that even though many of their light curves did in fact rise to their peak on a timescale of about a month, about looking quite a bit like the fallback time, and then subsequently decaying in the optical around t to the minus 5/3, the temperatures were too cool. In other words, the luminosities in optical peak were 44 to 45 ergs per second, but the temperature of that emission was substantially less than what you'd expect either for disk emission from the ISCO or from even the circularization radius. As stated another way, the photosphere radii are much larger than either the ISCO radius or circularization radius for a sample of TDs from Subi's review here. And so, broadly speaking, some of the proposed solutions we've heard about is that the optical emission has nothing to do with black hole accretion. It's due to some colliding stream, which should also maybe happen on the fallback time. Or maybe we actually are feeding the black hole at a rate which faithfully tracks the fallback rate, but it's being reprocessed by some extended outflow or envelope. And we've heard very nicely from Jane the other day about the latest simulations of this type of scenario. Where you have reprocessing of the central accretion luminosity by either a slow outflow or a weakly bound sort of torus. I used to believe that maybe this was a slow outflow based on the sort of weakly bound nature of this torus, but I do think now we have some evidence that, at least a substantial fraction of star eventually has to accrete, because as Stuart said, if we look at late times, we see this a lot of emission UV X-ray coming out. The missing energy problem is in some sense solved if we look in the ultraviolet at late time. So we need a substantial fraction of that half of the star that's bound to accrete, or we're going to run into problems. So not everything can be ejected in a wind. And I think Tatsuya has a nice paper showing actually if you try to create a photosphere from an unbound sort of outflow, you run into some mass problems. And so while I believe there certainly are outflows from the circularization process, they may not be carrying away most of the stellar material. But this picture, I really like this idea that there is, viewing angle dependence to the X-ray emission and optical emission when we do have this type of geometry. But the thing is, in most of these reprocessing scenarios, it seems like the sort of assumption is that the reprocessing is tracking again faithfully the fallback rate. Matter is falling back, and somehow it's immediately sort of going into that inner accretion luminosity. And therefore, when we see the optical peak, we are seeing when the black hole is accreting at its maximal rate. But I think there's, at least been some hints that there may be cases of delayed supermassive black hole feeding. We already heard from Yvette nicely these examples where it seems like the sort of powerful outflows may be turning on at very late times in many TDs, unexpectedly late, several hundred days or even 1,000 days after the event. These could be off-axis jets that were launched promptly. I'm a little skeptical because of how narrowly, tightly concentrated those jets would be, but we'll hear later about that possibility. But it's suggestive maybe, certainly the jet is coming from very close to the black hole, so why is it turning on so late? We also have heard about the fact that we oftentimes see the X-rays delayed in their rise relative to when the optical is peaking. Sort of ironically, when I was working on reprocessing scenarios, this paper by Ayer and Suvi were arguing that it can't be a reprocessing scenario, that it needs to be delayed accretion because they don't see a change in the X-ray absorption column. But this could also be, it could be a situation that Jane described where the opening angle of the funnel is growing, which we see more and more X-rays, or it could be that it's actually taking sizable time for the accretion rate to peak onto the black hole. A much more controversial thing is we haven't discussed yet at this conference yet, but there are claims of possible neutrinos associated with TDs. The neutrinos are almost certainly, if they are real, almost certainly coming from near the ISCO of the black hole, maybe the corona of the accretion disk. But they're not coming right at the peak of the optical. They're coming sizably later. So maybe that's evidence. All of this that maybe we're feeding the black hole after some delay relative to when the optical is peaking. And so why would that be delayed? Well, one thing that's been discussed quite a bit is that maybe it takes a while for these streams to actually efficiently collide because of precession and other things. But I would say observationally, I've never really bought into this too much because, as I said, when we look at it's clear that these TDs are very quickly creating a lot of emitting surface area, right, on roughly, a few fallback times at most. So nature didn't wait, at least in the events we see. Maybe there are events where it does wait to circularize. We've also heard recently that there may, in some cases, rather controversial again, that may be rapid circularization. This is a paper by Elad Steinberg and Nick Stone, where they find that even for a vanilla beta equals 1 tidal disruption of a 10 to the 6 solar mass star, within about 1 fallback time, they find substantially more dissipation at the nozzle shock. So the matter coming out is very thick and very quickly sort of collides with the ingoing stream. And so after about 60 days, at the end of the simulation, you end up with most of the initial fallback material in this kind of quasi-spherical bound structure around the black hole, which has a characteristic radius of 10 to the 15 centimeters. So quite extended. It's actually comparable in size to the apocenter radius of the most tightly bound debris, with a density profile that's something like 1 over r. So in fact, most of the mass in this spherical envelope that's been formed around the star is actually on large scales. It's not down close to the black hole. So I would say circularization is sort of a bad term in this context because what we're creating is not really something that is mostly disk-like. It's more spherical-like. It's more star-like. And so this got me thinking, maybe we can, and this is not exclusively my idea, but maybe you can think about TDEs as sort of somewhat akin to hydrostatic stars for a period of time. So as I mentioned, the half of the star that's bound to the black hole is bound by that energy. If you were to construct an envelope in hydrostatic equilibrium with a radius using the Viral theorem, that's what you would need for that binding energy. This is what you get, basically, the star's radius times the black hole mass to the star's mass to the 2/3 power. So it works out to be around a few 10 to the 14, 10 to the 15 centimeters. So in other words, just creating an envelope with how tightly bound material is from the disruption produces something which actually is rather similar to the peak black body radii. This is from Yao et al. You can see that Johan's paper that I'm not saying this is a tight correlation, but it's sort of just taking this naive estimate and overplotting the data. It actually is comparable to the observed photosphere radii. And of course, however, this virial radius of this structure is actually, self-consistently quite a bit larger than the circularization radius by the black hole to the star's mass to the 1/3. So this is, a factor of typically 100 or something like that. This structure is not it is necessarily slowly rotating. If all the mass were down near the circulation radius, then by definition it would be rotationally supported, rotating at Keplerian, but in fact it's much larger, so it's rotating highly sub-Keplerian. So this envelope is necessarily supported by turbulence or thermal pressure radially versus some kind of rotationally supported disk, at least on the large scales. And this has a sort of basis for some old models for TDEs, Loeb and Ulmer, and also Eric and Mitch Bagelman have these zebra models, and this is very similar to the outer structure of what they call zebras. So the question is, what happens next? Let's say that I don't know how circularization, sphericization happens, but let's just say it's a mess, there's collisions, there's shocks, I create something where it doesn't have time to cool, create this structure, how does it subsequently evolve? And so that was the motivation for this so-called cooling envelope model, this being the envelope being surrounded by a disk in the center, and the model essentially follows the evolution of the mass and energy of the envelope. So you're allowing mass to be added to the envelope from fallback accretion. I'm assuming it comes in and dissolves in the envelope. You're allowing actually accretion onto the black hole, but at a rate that depends on the density down near the centrifugally supported part of the system. Assume a density profile for the envelope. Then you're also tracking the energy budget of the envelope. These are hydrostatic structures, so which are radiation pressure dominated, so they have to radiate at the Eddington luminosity. This is basic stellar physics. But I also allow there to be a source of fallback energy. So if you allow some matter that does fall back and circularize near the apocenter to contribute also to the luminosity. And then, as I said, you can also track. You can also allow for feedback from the black hole accretion onto the envelope with some efficiency parameter eta. So what the model does is, in terms of these parameters, it basically predicts it doesn't say how you form the envelope, but once you form it, it tells you how the radius it should change with time, its luminosity, effective temperature, and also how the black hole accretion rate should evolve in time. So I'll just say one of the main punchlines of this is actually what we found is, in many cases, the envelope can actually cool from the outside faster than it's able to accrete from the center, meaning that the rate limiting step to actually getting mass into the black hole isn't how fast the inner disk can process it into the black hole. It's how fast this envelope is able to cool and contract and basically raise the density near the black hole. And in that case, the rise time of the accretion rate is actually set by a cooling time of this structure, although it can be also delayed, the cooling, by energy injection. So let me just go through the simplest case, which is pure cooling. So I create an envelope. I don't consider any additional, most of the mass is coming back in a few fallback times, so I don't worry about any additional mass of energy or material. As I said, it has to radiate at the Eddington luminosity, so you can define a Kelvin-Helmholtz time, which is the initial binding energy of this structure divided by the luminosity. That coincidentally works out to be about a month as well, similar to the fallback time, albeit with a different dependence on the black hole mass. So it's radiation dominated, so as the envelope contracts, its radius goes as 1 over time. The effective temperature, given a fixed bolometric luminosity, rises roughly as t to the 1/2 power. And if you're below the Rayleigh-Jeans tail of the optical emission, which is peaking, as you can see here in the ultraviolet, then you would predict that the nu luminosity should basically go as the temperature times the radius squared. So this goes as t to the minus 3/2. So this leads to a number of predictions. It predicts that when I'm in this cooling envelope phase, more luminous TDEs should arise from more massive black holes. After the peak, the photosphere should contract as the envelope cools. It should be getting slightly hotter in time, fairly weakly, and that in the optical at least, the light curve should decay in a way t to the minus 3/2, which is coincidentally similar to fallback. But none of this is fallback physics. It's just, there is fallback contributing in the actual model, but just an envelope of fixed mass contracting also gives you something like that. So let's go through some of these predictions. I'm not going to have as careful of comparison as Short, but I will just put up a few of these correlations from Yuhan's paper between bolometric black body luminosity and black hole mass, or what was a proxy for black hole mass. And there does seem to be a correlation, as Short described, between more massive black holes do seem to create things. And this is, as I said, just a consequence of hydrostatic equilibrium in this envelope. Photosphere radii should contract and get hotter. Again, these are some papers from Short's. Indeed, I don't know what's happening. Yashan and Kaman can tell me how the debris circularizes, but But after that, you do see something that looks like it is contracting, and then looks like it is getting hotter in time. What about line widths? Well, as Short says, line widths may be due to electron scattering, but this envelope, if it's truly sort of star-like, it has to be able to carry out that luminosity, for example, through convection. So you can estimate, given the density of the envelope and the luminosity has to carry, how fast should be the convective motions in the envelope. And you get several thousand kilometers per second, which isn't terribly different than the observed line widths in TDEs. Of course, this would be, the outer parts of the envelope are not rotationally supported, so this would be more sort of chaotic velocities, not necessarily some kind of double-horned disk profile. But these convective speeds you require, because it's basically requiring a star to carry the Eddington luminosity of a black hole. These are incredibly fast, almost sonic convective speeds you have. One of the interesting things, one of the consequences for this is that this envelope may be a great place for amplifying magnetic fields on small scales, and also the envelope is rotating, so you may be able to get an alpha omega dynamo if you're interested in how we create the magnetic flux, which then feeds the corona and the jet. This may be a good phase to do that. So here's an example of applying the actual model. So there's 5 parameters of the model, and I would say they're all sort of physically motivated parameters. They're not things like we don't understand the physics, so we're adding some parameters. Although there is many things that physics we don't understand. But so you have the black hole mass, the star's mass, the penetration factor, and then you do have this, yes, you do have uncertainty feedback. How much of m dot c squared goes back into the envelope, and what is the viscosity, which only really matters in cases where the rate limiting step is the viscous time to getting mass in the black hole. So, for example, more massive stars produce brighter TDEs because there's more matter that's contracting and releasing gravitational energy. In this model, one of the flaws, I would say, potentially with respect to the data, is lower mass black holes do actually tend to produce longer light curves in some cases because it takes longer for the envelope to cool. But if you add things like feedback, you can actually get kind of plateau-like phases where essentially the black hole's accretion energy is sort of balancing the contraction of the envelope. So it contracts for a while, and then it just sits at a constant size where it's turning the accretion energy into luminosity. And then this is just showing and then as I said, these models also predict how the accretion rate on the black hole is rising. And you terminate the model once it contracts fully to the circularization radius. So with Nick Serin, I learned about TD is that if you want people to take your model seriously, you have to put it in a form where they can actually use it and apply it to data. So Nick coded up this simple cooling envelope model. We have a phenomenological rise to the model, and it's basically mostly fitting the decay phase. We applied it to 12 ZTF TDEs as a proof of principle. And I'll just show you some of the posteriors that we got on different properties. This is the black hole mass, the star's mass, penetration factor, and this is the time it takes the envelope to contract to the circularization radius, compared to some theoretical on the bottom, compared to some theoretical expectations, for example, to the IMF you might expect, or to the rate of TDEs with black hole mass. And I'm not claiming anything that, I will say it is nice, but mostly we have fewer TDEs from more massive stars, although there may be in excess of more massive stars consistent with some things that Brent has found. But anyways, I don't want to make too much of this, but you can apply it to data, you can explore what the implications are. What I want to say, though, is that in this particular case, the envelope is, when you get a peak in the X-rays is essentially when this envelope completely contracts to the circularization radius. This is a transformation from a quasi-spherical structure into a disk, which can then do maybe the spreading evolution that was described. So roughly speaking, if you again neglect any feedback from the black hole, the time it takes for the envelope to contract is basically the initial Kelvin time times the ratio of the initial size to the tidal radius, and it turns out that this works out to be about a year, weakly dependent on the black hole mass. And so I think it was, at some point asked, why do these plateaus turn on at this time? Why do we, see various rising evidences of black hole activity at late times on this time scale? I would say it comes out pretty naturally from this type of consideration. And then, as we've already heard, at late times, it could be that we're seeing unobscured accretion disks. So in other words, it contracts and then it will viscously spread again. So before I finish, I'm basically done. I'll just say maybe all this is wrong. So I have to pitch, another idea in case the first one is wrong. If you're around next week, I'll talk more about this. But maybe I'm wrong, and maybe we do actually feed the black hole faithfully from the fallback rate. Is there any other way I could get delayed the escape of jets from these systems? And so this was work with Udila Tabul as a graduate student at Hebrew University. And the key point of this very different topic is that when you disrupt a star in general, the disk of the disrupted star or the star's orbit will be misaligned with respect to the black hole spin. And since these are thick accretion disks, thick disks tend to undergo lens-tearing precession around the spin axis of the black hole. So even if these disks created jets, they may not be able to get out of the environment. Because if you think about it, if it's precessing around on a time scale of 1 day, in any given direction, if there's a disk wind, the jet would have to encounter a direction where there was disk material flowing out earlier. And so modeling this kind of time-averaged disk outflow as a spherical structure with Udila, we showed it was perhaps not unexpected. As you go to larger misalignment angles, you need a more powerful jet to be able to escape from the envelope. And so what we believe in the system is as the disk becomes thinner at time, it will get easier for various reasons to align the disk with the spin. And so it will get easier and easier for a jet to escape. And so there may be ways, particularly when the black hole doesn't have a huge amount of magnetic flux, it may be delayed in terms of when it can finally escape. On the other hand, the jetted TDEs could have, those would be cases where the black hole gets a lot of magnetic flux and the magnetic field itself causes the jet to align quicker, and also it's easier for a more powerful jet to get out. So this could potentially explain a dichotomy between jetted TDEs where the jet gets out and aligns with the spin very quickly, like we saw in J1644, versus more delayed jets that only get out after a year or so. Okay, with that, I'm going to assume I'm basically at the end. Oh, wow, only 22 minutes. I talked way too quickly, but that's fine. So maybe I'll take a few minutes and just talk about the takeaways. So I think my takeaways are basically, I'm not convinced that rapid spherification, and we use circularization, necessarily implies we can get mass down to the black hole quickly. It depends on where it goes. If these streams deposit all their mass down near the black hole, then sure, maybe we can force feed the black hole, get something right away. But if it's on large scales, it's not clear to me that there doesn't have to be something else going on. Because the debris is weakly bound, it wants to form this large structure, which I think is necessarily pressure supported. And I think just taking the size of this envelope that you get naturally explains the size of the optical photospheres. And at least if it's, the black hole is a small target in the center. It's hard to get mass into that, and so it's much more efficient to cool from the outside and push mass inwards that way, I think. So just to be clear, in shock scenarios, what heats up the envelope are the shocks. So in some sense, the luminosity source is the shocks. But then subsequently in this scenario, as the thing contracts, basically the energy we're getting out in the optical flare is the energy released as you contract from this viral radius down to the tidal radius, which works out to be around, I scared something here, it works out to be around 10 to the 52 ergs or so. And if you just consider this contraction alone, as I said, you can actually get things in the optical band that look of order like t to the minus 5/3. I've already talked about most of this. I think this may explain why we see delayed activity. There are a few predictions which I agree are in a little bit of tension with the data. I don't think these envelopes are as relevant to high mass black holes because the Kelvin time is very quick. So I think for higher mass black holes, it may be in fact the case that if we form a disk quickly, we accrete at the rate of the fallback. They become more important for lower mass black holes because the Kelvin time actually gets longer. So the prediction is if I go down to really low mass black holes, 10 to the 5, 10 to the 4 in this scenario, they don't actually, you would guess based on the fallback time that they would have quick TD light curves. This is saying they could have slow TD light curves because it takes their envelope longer to cool because they're much denser. So I think that, as Short said, you're not really, you're actually seeing that the decay in these does seem to continue to grow with the black hole mass, which is a little bit in tension with this. But I think it really depends on how we connect this on, the initial conditions and how we connect, how long it takes to build up the mass of the envelope. So I think what we really need to address this are really long-term radiation simulations, like the kind that Jane presented, but something where we can do it in a global context, where we're understanding how the streams, where they're feeding mass to these disks, and what is happening at the outer parts of these disks, which are probably pressure supported. And when we see a plateau, I'm pretty convinced that it's reached a disk phase and is spreading. I agree it's a great idea. But on the other hand, in this scenario, I can also get a plateau where I can get a sort of an envelope that is still puffed up by energy input from the black hole. So to really test whether I have an envelope which is a fixed radius, which is being held up in size by accretion versus a spreading disk, I agree with Elliot. It would be great to look in the infrared to see some evidence that we're actually growing the outer photosphere of this structure when we see the plateau phase. So with that, I will finish and take questions. Thanks.
Elena, go ahead.
Hi, Director. Thanks. So this envelope are radiation pressure dominated, so weakly bound, and therefore in the outer layer, in the radiative layer, you expect mass loss, perhaps from radiative-driven winds,
Right.
and the mass loss then mass loss rate can compete with the accretion rate, or even the mass loss timescale may compete with Kelvin-Helmholtz timescale. What are your thoughts on this?
Yeah, no, I agree. I agree that in principle this envelope probably has some type of wind from it. As I said, if we go to late times, we don't see a lot of, if we integrate all the light emitted by TD, we recover a lot of the accreted mass. So I don't know if these winds empirically could carry away a lot of mass. What I will say, though, is that if I go to lower mass black holes, like 10 to the 5 or so, so what I've assumed is that this stream deposits its energy near the apocenter of the stream, because Clement and others have shown, you've shown, that these streams tend to be more susceptible to dissolution in the envelope near their apocenter. So I've assumed that they deposit their mass near the apocenter. So this provides a power source to the envelope. What I find as I go to lower mass black holes, this can become super Eddington, and Elliot has shown that when you heat up an envelope at a super Eddington rate, it starts to put that energy not into radiation anymore, but to driving a wind. So my guess is these winds become more powerful as we go to lower mass black holes, where this matter that's being added to the envelope is depositing energy super Eddington into the envelope. But it could be present even in these cases. Yeah.
But I think you can calculate mass loss rate and then
from the luminosity of it. Well, yeah, it's the same issue you would have with massive stars, but even much messier. But yeah. Thank you.
Thanks.
Yeah.
Clement?
I have a question regarding your new calculation.
Yes.
I think it was one of the first takeaways you mentioned that this large envelope radius would result in a large optical photospheric radius, but this is not directly. It's not necessary.
Yeah, the envelope radius isn't directly the photosphere radius.
Yeah.
So
I was wondering like how much you would estimate the optical luminosity making this assumption.
Yeah, I mean the photosphere scales, the radius scales with the size of this envelope for some structure, for some structure of the envelope. So so you're right. That's why I put a scaling here in the actual paper. When I calculate the photosphere radius, I just have a structure that connects the inner part of the star with the photosphere. So the photosphere is a factor of a few times larger than this. This is like the characteristic size of the star versus the photosphere.
I meant the comparison between the scattering photosphere and the optical photosphere.
Oh, okay, yes. I have not included that. Yes. So you and Wenbin have pointed out that the scattering photosphere. So yes. So one would have to include the color corrections for that. I have not done that yet, and I agree that.
Do you have an idea about how much the optical luminosity would decrease compared to? Or maybe
These, these are electron scattering opacities, so one would have to figure out. I have not done that yet, but it's a good point. Yeah, thank you.
Thanks.
Hey, Brian. Nice talk. I'm really interested in thinking more about the implications for like when you would see X-ray emission and what kind of time scale, you know, what kind of luminosity you might expect given different cooling times or something like that. But I mean, just generally, in your model, like how do you explain, you know, the eRosetta TDEs, for instance, where many of these
don't have any optical.
Like where is that just like a higher penetration?
Yeah, so my picture for the X-rays is very similar to what Jane has proposed, that they're coming from this polar funnel. To completely suppress the optical emission, you'd have to have this envelope basically not be present. So the two ways to do that, one would be to go to a higher mass black hole where this cooling time is very short, and then you don't get this phase, or to go to a lower mass star where the cooling time is very short.
Okay.
Or maybe a more bound star that is more tightly bound when it's disrupted, so it doesn't want to form this big structure. So I guess that, yeah, well, one of those would predict more massive black holes for the eRosetta, but I don't know if that's...
And then like a much faster cooling time would then lead to a much higher m dot, like, you know, higher...
Yeah, ultimately you're related by you're limited to the fallback time. So this, yeah, you're right. You could get a higher X-ray, yeah. But ultimately, in the limit where this doesn't exist, then it just becomes the usual situation of matter falling back, feeding a disk, and it making X-rays on that time scale. Thank you.
Hey, Brian. I have a similar question to Aaron, actually, but on partials and partial disruptions. I guess looking at this, my intuition would be that the timescale would also be far shorter if you deposit.
Yeah, if you fire less mass, it should, yeah. So the prediction would be that maybe partials should more faithfully track the fallback.
Yeah,
and then there wouldn't necessarily be this envelope.
Would it then also indicate potentially faster disk formation? The reason I ask is that there are these cases of double-peaked lines where partial disruptions are inferred.
Double-peaked lines or
double-peaked emission lines in the optical.
I see. So yeah, I think if you're seeing a double-peaked line, then you're seeing a disk-like structure. So you're probably seeing something where the photosphere is in a region which is rotating quickly. Yeah. So my guess would be those would have to be lower mass. You know, those are what you get if you have lower mass stars or partial disruptions. Sure. More likely.
Great.
Yeah. Awesome. Yeah. Thanks. Hi, Jane.
Hey, Brian. Very nice work. So I have two quick questions. The first one is. Because our total luminosity is L Eddington plus L fallback, does that mean the bolometric luminosity is always super Eddington in this model?
I included that. It can become the fallback. Yes, the fall. That was what I was attempting to say a second ago. Is that this fallback luminosity can in some cases approach the Eddington luminosity for lower mass black holes. I generally find that it's a correction it's not really changing things a lot because I'm assuming that the matter is incorporated at the fairly large apocenter radius of the debris. I'm not putting this accretion luminosity down near the black hole. But yeah, definitely if you go to lower mass black holes where this is higher and this is smaller. Well, no, it's not smaller, but this is higher. You can get super Eddington accretion, super Eddington heating, and then I think that might give more powerful outflows from these disks. And one can speculate maybe there are cases where the photosphere is actually in the outflow, and I don't know if that can explain, for example, these featureless TDs or not, but that's been discussed a little bit. But that would probably happen preferentially around lower mass black holes.
Okay. And the second question is, can you elaborate a bit more on what's exactly regulating the accretion rates in this model?
Yeah. This is quite contentious. I've been discussing this with Elliot. In this scenario, I basically have an envelope which has a prescribed density profile. And what I say is, okay, most of the mass is on large scales, and then as I contract, my normalization of my density near the circularization radius rises. And then I basically say, okay, the accretion rate should scale roughly as the density of the gas, basically the mass that is on the scale there divided by some accretion time. But that may not be the right physics. It may be more like a convection-dominated accretion flow where you're sort of feeding mass in at this scale and only a small fraction is getting down. But this is why I think we need to do the actual simulations to understand better what is this, what is the feeding rate, and how does this envelope evolve? I think based on the initial conditions, that mass has to be on large scales, but as it evolves and becomes convective, it may try to change the density profile, which puts more mass on small scales.
Okay, thanks.
Yes.
Thanks, Mike. I was wondering about this picture of the precessing jets.
Yes.
And as a way particularly to get the jet coming out later.
Yeah.
Presumably this would limit significantly the amount of energy that you can get in the jet that eventually comes out. Have you estimated how much of an effect this is?
Yeah, definitely. Like, if the jet is not coming out until 10 fallback times, then the sort of even if you had a MAD at that state, you could only get a jet with 10 to the 51 ergs or something. I don't know what the number is, but yeah, it definitely. So it's predicting this dichotomy. It's basically saying if the jet has a lot of magnetic flux, it has all the advantages. It aligns with the spin quickly. It easily breaks out right away. I get to see it right away. If it's weaker, it has trouble aligning, and when it does get out, there's less energy to power. So.
Yeah. So it's both the breakout process that limits your energy and the fact that
it takes. Yeah, exactly.
Happens.
So it kind of produces this. This is a different eta, but it's the L jet over m dot c squared that you need to break out.
I suspect that ultimately this would be the way to differentiate between these late time.
I see. Yeah, I see. You're saying if you measured a huge amount of energy in an off-axis.
Because
if we can robustly measure the energy, yeah.
Exactly.
I think
it
that
should come out eventually.
Right. Okay. Yeah. Very good. Yeah.
Yeah, Muriel.
Yeah.
Okay.
I noticed that your predicted X-ray light curves are always delayed. And how do you account for the sources that are optically discovered, like assessing Fortune Li, but have a prompt, very bright X-ray emission?
I agree with what's been said, that I think the formation of the envelope, these early shocks, I think you can get X-rays from the early phase of this before you've created the envelope, is my guess. I mean, that was what these simulations also by Elad and Scheinberg and Stone
But even 10 to the 44 X-ray?
I don't know if you can get that bright.
Yeah, because there's a couple optical.
I think there is a disk in these scenarios that's happening. There is some part of the structure that's a disk, and until you've created this structure, you should be able to see down to that more compact scale.
But they also have a bright optical emission. Like Assassin Fortune Li has both 10 to the 44 in optical UV and X-ray at the same time.
Okay, so that may be one of these cases where I need to. What's the black hole mass?
10 to the 6.5.
10 to. Okay. Well, I guess I would have said that was a low mass star or a more massive black hole, so that this envelope is cooling very quickly, and so I can get matter down to the black hole. But I don't know. I don't want to make up something for your event.
Wenbin?
Yeah, I have a question on this, the two time scales. So there is the cooling time scale, which is 20 days for
the initial cooling time. Yes.
Initial cooling time scale, exactly. That's all that matters. And then there's the fallback time.
Yes.
Right? If your cooling time is shorter than the fallback time, then you should not form such an envelope. Right?
That's the initial cooling time. As the envelope begins to contract, the cooling
but
time.
It would not form at first place, right? Because the cooling time, if it is shorter than the fallback time initially, right?
Yeah, I mean, this is the cooling time to radiate, to go from the Vero radius to half the Vero radius.
Uh-huh.
So I agree. You wouldn't form. Yeah, you're right. You wouldn't form that structure at the full potential size.
Exactly. Yes, right.
But then as it contracts, the cooling time gets longer. So you would always meet at a size where the cooling time of the object was the fallback time.
Yeah, looking at the cooling time, which goes down with black hole mass, like the second equation here, and then the fallback time gets longer with black hole mass. So the expectation is that for, let's say, black hole mass more than 1 million solar masses, then they already meet, right?
Yeah, if I go to certainly if I go to 10 to the 7,
10 to the 7 would
even
be...
the cooling time for an envelope which has 1/10 of this size, yeah, they would be becoming comparable to fallback time. But it
would be a smaller envelope.
You would have a smaller envelope
That's
at the
right.
beginning, yes. So yeah, this one should be careful in making this statement that there should be some events that.
Yeah. Okay. Exactly.
But here I'm just plotting the Vero radius, not the photosphere radius. So anyways, it's a good point. Yes.
Thanks.
Thank you. Okay.
Yes, this may be a naive question, but can you briefly say what are the main physical differences in assumptions and therefore structural parameters between your envelopes and the old Loeb and Ulmer envelopes that look to me quite similar, superficially, but what are the main differences?
Right. So Loeb and Ulmer just assumed irradiating at Eddington. I don't think they considered this evolution of the envelope. It's been a long time since I read the paper, but I don't think they also assumed a density profile which put all of the mass very close to the black hole.
What's the physical difference?
I don't think they thought about there being an inner disk at all. I don't think they thought about there being an inner disk at all. And they don't consider the cooling. They just said, I'm forced to radiate at Eddington, and I irradiate at Eddington until I emit all my energy. But they didn't say how the radius of that structure is changing. So they weren't really creating light curves. They were creating bolometric light curves, but they weren't really following how that evolves.
Okay.
But I have to go back and read their paper. Yeah.
Okay.
It's not terribly different. It's
Joachim?
Yeah. So I'm wondering if, have you thought much about the implications of this model for QPEs following maybe optically bright TDEs, where you have like the stellar M radii that are well outside the compact disk, but maybe like, does it survive the creation of this extended envelope or interact with it in any interesting way?
I haven't thought about that. The envelope is pretty low density, so I don't know if it would cause significant, it lasts for very long. So I don't know if it would cause, for example, substantial drag on an emery that happened to be. It's a good question, though. It's worth looking into. My guess is it doesn't care a whole lot that there's this envelope, but.
Okay, but it wouldn't change the structure of the star in any appreciable way that you might see.
Yeah, I mean, the star would be going through this envelope, but I don't know if it would be terribly more or less destructive than the disk phase that follows for decades. But we can look into it. Thank you.
Okay, if there are no more questions, let's thank Brian again.
Thank you.